Okay, so this is about anomaly detection using neural networks. I'm from BlueVine. What BlueVine is doing, we are an online lender, basically sort of a bank for businesses in the United States. We give small and medium-sized businesses, we give them loans, and basically loan requires risk. So what data science in BlueVine is doing is bridging the gap between fast and risky, right? Because I can take 20 people, give them a week to research someone, and then they would give you the safest loan there can be, and I can give a person just look at them for 1 minute and give them a loan, but then that would be risky. What we are trying to do is bridging the gap to give them a fast loan, still minimizing the risk. What we're doing, we're building credit models. We analyze financial strength of our businesses. We incorporate third-party data. That's a lot of what we're doing, and we're making data pipelines for the entire thing in order for us to have a lot of information about each user that joins our system. So basically, this is the holy grail of data science, right? If we had a line for every user, a row for every user, and then we had features, then we could just deploy a lot of models and get a lot of information, but that's hard, right? We don't get that out of the box. This is not a job interview. This is not academia. What we do have is this. We have a lot of data sources. We have them. We have some primary data sources. Those are the light blue ones. We have the medium blue ones that are some intermediate models, right? If I can see a person's bank account, I can sort of rank the bank account, but that would be an intermediate model. But then we have higher level models. This would be like something like what we call the BlueVine score. That's basically a score that will give a business to see if they're eligible for the loan and at what terms. So each model is taking a lot of information, but that information is not, again, as you see on the right, it's not white data, clean data. It comes sort of as a streamlined data that only then becomes what we like as a row-based table. So basically, this is where I come in, because this is where everything can go wrong. If some party doesn't give us data for some time, if some data tables have changed in the databases, I might not know about it, and that would be a problem. The thing is, you might say, well, you can just see that something is stopped working. Well, that's correct for some of the cases. On some other cases, I can just stop receiving data and use old data and think my models are amazing, but they're not because they're not using updated data. So basically, we have like 1,000 different variables, or a few thousands different variables. Some variables are just primary, some are intermediate models, some are more complex, and each one of them can have its own problem. So we're talking about a few hundred variables can have a few hundred models, right? I can't have one model that detects anomalies for all the variables on the get-go. And all the variables are different. Some are numeric, some are text, some are categorical. Each one can behave differently. Some write once a minute, some we just get once a day, some once a week. That might be a problem. So we need to get a lot of different models, and we need to monitor all those models and see and find the anomalies in order for us to catch them as quick as possible. So we started exploring what does it mean to have an anomaly, right? Because anomalies can be if I stop getting the data at all, or if I'm starting to get, I was expecting values of hundreds of millions, and now I'm getting just, I don't know, tens of thousands. That also would be a problem. So what we started is we thought of, let's just count the data and see if we're still writing to the database, being it from the outside or being from our internal models, if we just write the number of writes to the database for each variable that we use. And we understood it now, like what's the frequency, right? If I can measure how many writes in a 15-minute period, how many writes in a 1-day period, and you can see here that for the same variable, for the same number of writes, it looks different depending on the frequency of the summation. The summation part is also another thing, right? because the data is not summed up. We just get streamlined data of timestamps, and we need to sum them up. So we decided to take it once an hour, just take all the variables once an hour and count how many writes to the database there were. And so we need a few services to do this. We need one service. We do it in microservice architecture. I'm saying it in quotes because I'm not sure that CS like the official definition of microservice is what we're doing. But there's one service that counts the data, one service that just trains the model, one service that predicts, and one service that eventually, when we say something as an anomaly, we say, OK, let's alert it, right? Because just writing anomalies to the database, that's not interesting. We need a human eye to now look at the anomalies and think, why did they happen? So we start with the count data, right? So we have a count service. We just, once an hour, we take everything, we count it. And we can see that here we have 3 variables, for example. You can see them, they behave differently on weekdays and on weekends. We need to learn that. We can see that they act differently, right? The purple variable is a lot lower than the orange and blue one. And if we take another variable, that's another different world, because it writes differently on the weekends than the other ones, right? It's right about the same like the weekdays, and also it writes a lot more. We need to learn that. So we have a lot of variables. Imagine now we have like 5,000 of those, and we need to treat each one of them separately. What we're doing is we're taking, for each variable, we're taking about 7 months into the past. We can take indefinite time in the past. I decided on about 6 months of training period, then 1 month of testing period. The testing period will come back later when you want to. That's an anomaly. OK, so this is just one variable. Imagine we have 5,000 lines like that. And all of those need to go through some data cleaning pipeline, right? Because we have some. It's the same slide still, so hoping for the best. Anyway, we need to clean past data because we have anomalies in past data, and we try not to learn those, especially when we know about some variables, they have man-made anomalies, right? Maybe if this is a new variable, we just want to populate the data, the historical data. So there's one day that I could write maybe a few months worth of readings. So that wouldn't be good. We need to clean that, and we need to make this into a pipeline, because then when the later ones come, they would go through the same pipeline. So now we have data, and we created sliding windows throughout the data. I forgot to say about it. We created sliding windows. I'm looking a week back at one particular point. You're saying? So we're looking at one particular point, and now we want to predict that. What we're trying to do is we want to take the real value and the prediction and look about the error. If the error is too much, we can say this is an anomaly. So I've learned a fully connected neural network. We started with, when you say, let's learn time series, you usually start with LSTMs. We've started with those. They performed well, but they took a lot of time. And then I've read somewhere this is that for univariate prediction, you probably don't need LSTM. So that's one main takeaway that I had. You probably don't need LSTMs for that kind of job, and it learns 1,000 times faster. And now we don't have to pull this mass GPU thing in order to predict. We can do it on a pretty strong server that just uses CPUs. And we optimize for the mean absolute error, because we have a lot of variables that go to 0, and we want to learn those as well as the ones that are high. And eventually we can predict. So the prediction line is the orange one, and the real data is the blue one. It looks pretty good. The thing is, this itself is interesting, and we need to make it better all the time, but it's not the most interesting. What's more interesting is how the error progresses through time. And here, now you can see, you have, in the naked eye, you can see kind of like 3 things that look like an anomaly. Those are the differences between the prediction and the real data. We can take all those and create kind of a histogram. The histogram of the errors and it looks kind of like that. So most errors are close to 0. That's a good thing. And some of them are a lot farther. And now we have a histogram, and on the histogram, we can learn some distribution. So we fit a distribution. In this case, it's a skewed t distribution. And now that we have a distribution, we can look at the percentiles. If we go too far right or too far left in the error, that's probably an anomaly. And that's what we're doing. Now we're in the predict phase. Well, the first chart tells you I now have a new observation, right? The hour passed, I can count how many times I've written to the database this specific variable, and I have the data. Now that I have the data, I can predict what I would have expected if I hadn't seen it, and that's what I'm doing. So that's the orange line in the middle chart. And then I can look at the errors. Those are the dashed lines between the blue one and the orange one. And finally, I can plot those errors giving the thresholds that I've learned from the distribution that I've learned beforehand. And in this particular case, you can see that there's no anomaly in that kind of data. Although it looks weird, it's not very structured, but the network knows how to predict it reasonably. There's a case here. In this case, you can see that there is an anomaly. There's the far right one, the blue that goes all the way to the top. That's probably an anomaly, and we can see it by the fact that it's a lot more than the 99th percentile of the fitted distribution that we've created earlier. All of those are then saved back to the database, including the metadata for the model itself. And then now we have a database that says those are predictions, those are errors, those are the real data, and this is an anomaly. Now we have a list of anomalies, and what you can do with them is alert about them. So this is the interesting part for the team, because everything by now just happens all the time in the systems, but now there's an anomaly. So a data scientist can get that chart, and they will get that chart. That chart is basically doing one thing. Four things, sorry. It shows you the progression of the data and the predicted model for the last month and in the last 2 days. That's the bottom left one. It also shows you the underlying distribution, because there should be a marker in the arrow. I forgot to put that one. That's a new thing. But it shows you how far are you really from those thresholds. And it also shows you the progression of the error, right? Because if the error progression shows you that everything is an anomaly, and I can show you an example later of the bad predictions, then there's more chance that this is also not an anomaly. In this particular chance, I just want to tell the story. So in April 30, we actually had a bug, a human-made error that we've done, and we didn't see it because it was a silent error, as I said in the beginning. And those are the scariest, right? Because we started using data that we thought was okay, but it wasn't. And we can see that 4 days later, and that's just values being changed, but because the values are being changed, the counts data is also behaving weirdly because it affects other things. And you can see 4 days later, we are starting to see anomalies, but then a week later, we can actually see a big anomaly. That would actually would have made us really look into it and probably to find the error. The thing is, we didn't have that by then, and we found about it just by looking at data by our eyes, and we just fixed it just a week even later. And the last red ones you see actually are those. This is the UN fix that the system think is an anomaly because there was a human intervention. The thing is, if we've looked at the first red point after April 30th, we could have spotted it after 4 days instead of 14 days. That chart will send an email to the data scientist. Each variable has its owner, and the data scientist will get this email that says, well, you have an anomaly. This was the predicted data. This was the actual data. And this is the error. But the errors should be less. The thing is that I'm most excited for this hasn't been implemented yet. At the last line, you can see that I can actually ask the data scientist, well, is this real an anomaly? Like, please look, research that. If it's really an anomaly, say yes. If it's not, say no. Well, currently, I'm just collecting the data, but in 6 months or time or so, or maybe a year, I can go back later and now have supervised learning for those thresholds, right? Because I had a model. One part was supervised, the neural network part, but the other ones I just said, well, take the 99 percentile. That's a good guess, but it's not optimal. This would make it a lot better. Now I could have supervised learning for the thresholds and for the anomalies. I'll finish off with some examples. So this would be actually a good prediction, right? I had some anomaly a month before, but the new one, you can see this is an anomaly trail, I call it. This is an X and not a circle, what I can predict. So if I'm above the 99 percentile, that's an anomaly. But what happens if I'm just above the 95 percentile? For one time, that would be OK. But if I'm doing that for 6 hours or more, that might be a problem also. So we detect that, and I can send an email. This model is kind of weird. So it has a period, like 1 week, it has a lot of anomalies, and then another week, it sort of learns the anomalies. And if there was no intervention, it just says, OK, those are OK. But then a week later, it again acts differently. So you can see that, again, there are many anomalies on those bumps. And the last one would be the bad example, because I cannot cheat you for the entire presentation. Some variables did not work. Some variables require more attention. Maybe we do need to go back to the LSTMs. So those create many anomalies, and those I just shut off for the time being. I'm saying those are not working. They need better care, and we'll go back to them. That's it. I don't have a conclusion slide. This is me. Just to say, the main takeaway is that neural networks sometimes sound hard because, right, you have deep learning by Google, and that sounds something no one can do except for Google. But then this is a very small neural network, and still it creates a lot of value, just deploying keras and sort of serving those out of the cloud being someone else's computer, in this sense, Amazon. They're just serving the model. I'm looking at results from a neural network of keras, and I'm just serving results back. This is me. You can look me up. I'm the best combination of data science and dead jokes on Facebook. And I'm from BlueVine. We're hiring data scientists, so feel free.
Thank you, Dean, for the brilliant presentation. We have time for questions.
Thank you. Do you train a single model for all time series or a model for each one by itself?
So it's the same model structure, right? The same architecture, but each one learns at different weights.
How did you clean the training data from the anomalies in the past that you mentioned before?
So basic methods like looking at the IQRs, and we started with looking at about 20 of them and just seeing what works. For those 20s, I've gone by hand and just looked for spots, then deployed them. They were OK, and then I tried to think, well, how could I do this for 2,000 of them? And basically, at most times, even the cleaning by hand was just looking at those that are super anomalous and just taking them off. The ones that do not go to the threshold of the IQR, what I'm paying is that maybe I'm learning some anomaly, a weird anomaly that's not just like high values. Well, I'm OK with that because they happen not so often, so I'm hoping for the model not to learn them.
Hi. Could you maybe talk a little bit about the characteristics of variables you were able to learn and predict accurately versus the ones you weren't able to learn? So what were the characteristics of them?
Yeah, so I can basically go on and on about defining those in a well-defined manner, but I'll start with those that look nice are probably nice, and those that look bad are probably bad. That looking bad would mean we have many variables that just don't write to the database a lot, but when they do, it's something important, and then they would write 100 times, but that would happen once every few days, so I cannot predict that. That would also not in a fixed time frequency. That might be a thing. What we find out later is that if you're trying to predict something that writes to the database by design every 2 hours, but you try to predict for every 1 hour, that creates like kind of a saw. And that current model can predict that. It's an easy fix, but it's currently not active. So those are kind of the problems.
How often are you dynamically relearning the model?
How often am I relearning the model? Currently, it's about once a week. It's a new thing, so I'm not sure that's the optimal one. But about retraining, so I'm retraining it again. I'm just taking a 6 months period back, and I can take a new test data. But the test data, what I'm doing, I'm testing it also against the old model that learned about about a previous time in history, but it might behave better. So if it behaves better, I'm still using the old one.
Hi. Here.
Hi.
How often do you refresh the models, and how do you separate between anomalies that reoccur or prevent from the model from learning anomalies? Like if there's, you talked about a human error. So if someone does this, how do you know to separate anomalies than the actual change that happened? Is that clear? Or?
Yeah, so the first part was the previous question. They said they train them once a week or so. It's currently once a week. I'm not sure it's the optimal one, but it's once a week. The second part is, well, we have, currently I'm not doing a lot of it. But I'm planning on the supervised part. You remember I've said I can ask the data scientist, is this an anomaly or not? I'm currently defining what should be the answer. Maybe yes or no is not enough. So I'm thinking about it currently. But in the future, when I'm learning that would be probably fixed. That's like you can answer, well, that was a human error, or this was not a human error, but this was an outside process that we had to do, and it affects that variable, stuff like that.
Hi.
Hi.
I wanted to ask about the anomalies and any possible correlations between errors or error groups. Is there some sort of classification that you are able to do?
What again? I'm sorry, I didn't get
If
that.
you are able to take anomalies and detect some sort of trends and find some sort of correlations between anomalies and specific errors.
So not yet. It's fairly new. So I'm hoping for that. It would help when it's supervised. It doesn't have to be, but it's fairly new, so I didn't research that part.
Hi. Did you try, why did you choose neural networks, or did you try statistical methods like ARIMA?
You're not speaking to the mic, I'm sorry.
I said, why did you choose neural network methods, and have you tried statistical methods like ARIMA or decomposition, or more traditional methods, I would say, for time series forecasting?
Yeah, so we thought of that, and most times we actually, you kind of, in ARIMA, you kind of trying to guess this seasonality, and I didn't want to go over that for 2,000 variables, so you can maybe learn the seasonality, but that would be also hard. And then you start with something that sounds simpler than a neural network, but then you understand that you need to learn a lot more and create something more complex than trying to deploy a neural network. We tried to deploy, it worked well, so we say, okay, let's do it.
So let us thank our speaker again.
Thanks.